This is the last section, Section 4, for Lecture 2. Our two topics are how to handle bad data and Chauvenet's criterion. At the end of the previous section, Section 3, I posed the question, what option should we use for handling bad data values? The two concerns that we want to avoid are including bad data in our analysis or excluding good data in our analysis even though it might be unexpected data. Ideally, we would like to exclude all the bad data and include only the good data in information we use to make decisions, whether for process control or research. The three options presented last time were make a personal decision whether to include or exclude data, keep all the data, avoid making a decision, use it all, or use a statistical analysis-based method to make the decision. Having people make a personal decision about whether to include or exclude data raises a significant concern about personal bias in the decision. A personal decision may exclude good data because it does not fit the person's expected results, which leads to a bias. Keeping all the data means that there is a high probability that some bad data will be included and contribute to whatever decision is made or conclusion is drawn. Removing data because of blunders, errors, or mistakes should not create a bias. The guidelines for making these decisions should be developed and written down as part of the standard operating procedures and reported when the results are reported. A statistical approach eliminates the personal bias inherent in the personal decision option. If done correctly, it should reduce the chances of excluding good data while still getting rid of data that clearly is not typical and likely bad. In this class, we will use Chauvenet's criterion as the statistical method for rejecting bad data while retaining good data. Chauvenet's criterion is a statistically based procedure. It is used to evaluate individual data values from among repeated measurements. It is common to have a computer-based data acquisition system take 5, 10, 20, or more readings and average them. We can use Chauvenet's criterion to decide whether or not one of the 5, 10, 20, or more individual repeated readings is likely to be an outlier or a bad data value. Chauvenet's criterion assumes that the errors have a normal bell-shaped distribution. This is the distribution that corresponds to random errors. So Chauvenet's criterion is used to find a random error outlier among a set of repeated measures. The course packet provides additional statistical concepts and equations. It gives the equation that describes the Gaussian probability distribution function for a normal bell-shaped curve. Again, this corresponds to the assumed distribution of random errors. The Gaussian probability distribution function can be used to set a lower limit x of L and an upper limit x of U for a normal distribution. If a data point is below the lower limit x of L or above the upper limit x of U, there is a fairly high probability that the value might be a bad data value. It might not be bad, but there's a fairly high probability that it is a bad data value. The probability is based on the number of observations n, where the probability p is equal to 1 minus 1 over n. To balance the consequences of discarding good data and keeping bad data, Chauvenet's criterion adds a k term and sets k equal to 2, which is used to adjust the probability distribution. If we make k smaller, more data is rejected. Chauvenet's criterion sets k equal to 2, and the probability function that sets the upper and lower limits is given by p equals 1 minus 1 over k times n. The upper and lower limits are set using the student's t-test value, which is based on the number of the data values collected, the probability function, and the data's mean and standard deviation. The expressions are x of L equals average x minus the student t-test value times the data's standard deviation s, and xu, the upper limit, is equal to the average x plus the product of the student t-test value times the data's standard deviation s. Some comments about Chauvenet's criterion procedure. It is statistically based, so it removes the potential for personal bias. The procedure can be automated and programmed into data loggers or computer-based data acquisition systems. The procedure should be used only once on the data values in one set of repeated measures. Never apply the procedure twice to one set of data. To go through the process, you need to calculate a population mean and standard deviation. With those values and the student's t-test values, you can calculate the upper and lower limits using the equation shown. With those values and the student's t-test values, you can calculate the upper and lower limits using the equation shown. You have a two-tailed student t-test table in the course packet on page 2-13. To get the right student's t-test value, you need to know the number of data values included in the mean, and you need to know the two-tail probability. The two-tail probability value is p equals 1 minus 1 over k times n. The number of data values, n minus 1, gives the degrees of freedom for these problems. This gives the row of the two-tail student's t-test table to use, n minus 1. The column is obtained using the two-tail probability p equals 1 minus 1 over k times n. The correct column to use is given by 1 minus p equals 1 over kn. Let's go over the example in the course packet. We have 10 data values, repeated measures. So n, which is the number of data values, equals 10. The population mean of the 10 data values is 20.645. Note that during these calculations I include one more significant digit than in the data. Do not add more. The population standard deviation is 0.131 and the population variance is 0.01712. Using Chauvenet's criterion, k equal to 2, and given 10 data points, n equals 10, the probability value p is 0.95. When we go into the student's t-test table, we use the value of 1 minus p, which is 0.05. This will be the column we will use. To get the row, we use n minus 1, which is 9. So we want the student's t-test value for t subscript 9, 0.05. The first subscript gives the row and the second subscript gives the column. So if you go to page 2-13, go to row 9 and column 0.05 and find the student's t-test value to be 2.262. We then calculate the lower and upper limits using the population mean, population standard deviation, and the student's t-test value. X of L is going to equal 20.645 minus 2.262 times 0.131, which is equal to 20.349. The upper limit, x of u, is going to equal 20.645 plus 2.262 times 0.131, which equals 20.941. With the lower and upper limits, we look through the 10 original data values, looking for one or more data values outside the limits. If a data value is lower than the lower limit, 20.349, it is likely a bad data value or an outlier. If a data value is greater than the upper limit, 20.941, it is also likely to be an outlier. Looking at the original values, we see that the value of x equal to 20.97 exceeds the upper limit, and based on Chauvenet's criterion, it should be discarded as an outlier. If we remove the data value 20.97 and keep the remaining 9 data values, the new mean is 20.609, or after rounding to have only 4 significant digits, is 20.61. The new standard deviation is 0.0677, which is about 50% the original standard deviation. The new population variance is 0.00458, which is about 25% the original variance using the 10 data values. This is a common observation after applying Chauvenet's criterion. The population mean does not change much, but the variance and standard deviation change quite a bit. The large change in variance will impact the statistical analysis. One other thing to note is that many statistical books give one-tail student t-test values. In that case, use the column with 1/2 of the probability values, 0.05 in this case. This presentation discussed 3 options for deciding whether or not to include a data value. The other main topic was to introduce you to Chauvenet's criterion for identifying and removing outliers in repeated measure data. This concludes the presentation for Lecture 2. In class, you'll have a chance to ask questions and work on some problems to develop your skills for handling bad data. Lecture 3 will introduce you to uncertainty analysis and calibration.